second half of lesson 19. On Friday, we learned how to use Euclid's algorithm as another method to find GCF. Today, we're going to look at how to use GCF in some more real-life examples and how GCF can be helpful. At the end of the summer, I was very excited. My husband redid our kitchen. When we first bought the house, it was all pink, the kitchen. It took 10 years, but we finally got rid of the pink kitchen and got a nice new kitchen. Now, in the kitchen, this area on the wall, below the cabinets and behind your counter is called the backsplash. You want to put something on that backsplash to protect it and make it look pretty. A lot of people put tiles up. So my husband decided he was going to tile the backsplash. So we found these really cute little tiles. And if he filled in the backsplash with these little tiles, it was going to take forever. All those little tiles to fill in the backsplash. And the more tiles, the more money. And then the more grout, the more work, and so on. So we wanted to find a way to use less tiles. How could we use less tiles on the backsplash? To use fewer tiles, what could we do? Yeah, let's use big tiles. If we use bigger tiles, then we could use fewer tiles. But what we had to do was make sure that the tiles fit evenly. Because we didn't want a tile hanging off the edge. Then I've got a tile sticking out of my doorway. That would hurt walking into it. And we also didn't have our tile cutter. We lent the tile cutter to my father-in-law so we couldn't cut tiles. So we have to figure out the largest tile that we can use so that they will fit into this area. Okay? And that's where GCF is going to help us. And that's going to be the focus of our lesson today. So first we're going to see how Euclid's algorithm came to be. Now I'm going to tell you the truth, because I always do. This is going to be a little confusing, and it's okay if it's a little confusing because it's not the goal of our lesson. The goal of our lesson is to figure out the size of the tile and how many tiles for a given area. But let's just take a look at what Euclid's algorithm means. So if we had this area that was 60 inches by 100 inches. So and this is the picture that you have on page 81 in your notes. So it's 60 units by 100 units. We want to see how many times 60 goes into 100. Could I because that's what Euclid's algorithm does, right? The smaller number into the larger number. Does 60 go into 100? Yes, we have room for one tile. 60 goes into 100 once. And here's our tile. But can I use a second tile? No. So is 60 our greatest common factor? No. Because we have a remainder of 40. We could take our 40 and divide it into 60. Is that going to work evenly? No, we still have some left over. So then we take our 20 and divide it into 40, and then we have none left over. So according to Euclid's algorithm, our GCF is 20. Is that reasonable that the GCF of 60 and 100 is 20? Is that reasonable?
Yes.
Yes, because it's less than 60 and 100. 20 goes into 60. 20 goes into 100. So 20 is the GCF of 60 and 100. So using the GCF, we can figure out how many tiles we need for that given area. I know that was a little confusing, and I know I went through that a little bit quickly, but that's okay. We're going to focus on the next part of the lesson, and that's what's most important, okay? So here is our area of 60 by 100, and 20 goes into 100. So instead of counting by 1 unit, 1 unit, 1 unit, 1 unit, I would need 100. Do I want to put 100 tiles across the top? No. I don't want to use ones. I can count by 20s. 20, 40, 60, 80, 100. So if each tile was 20 units, does that fit evenly? And 20, 40, 60. Does that work evenly? Yes. So 20 is our GCF because I could break 100 into 20s and I could break my 60 into 20s. 20 goes into 60 and 20 goes into 100. So my tiles, I can use tiles that are 20 by 20. So each side of my tile is 20 and then they fit in this area. And 20 is my GCF. So the GCF tells you the size of the tile. The GCF tells you the size of the tile. How many tiles do I have to buy now? Because if I use 1-inch tiles, this is 60 by 100. The area of this is 6,000. If I used 1-inch tiles, I would need 6,000 tiles. So instead of buying 6,000 1-inch tiles, how many 20-inch tiles can I use? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many tiles? 15. I would much rather use 15 20 by 20 tiles than use 6,000 1 by 1 tiles.
Why did you do 60?
Doing one together, this is going to make a lot more sense. So turn to page 83. All right, we just looked at how GCF can help us. GCF lets us find out the maximum size of squares that will cover a rectangle. Whenever we solve problems like this, we cannot have any gaps or any overlapping squares. Of course, the maximum size squares will be the minimum number of squares, which means the bigger the tile, the less we need. The bigger the square, the less squares we need. So here we have a picture of a computer table that measures 30 inches by 50 inches, and they're going to cover the table with tiles. Does anybody have a kitchen table at home that has tile on it? Yeah, so that kind of idea. This is going to be a computer table, and we're going to cover the top of it with tiles. Just like if you look down at the floor, it's covered with tiles. Look up at the ceiling, it's covered with tiles. Okay, they're going to cover the computer table. So you have the picture in your notes on page 83, so you can label it 30 by 50. Just as a side note, what's the area of that? Bigger. 1,500 square inches. So if I use 1-inch tiles, how many 1-inch tiles would I need? Yeah, I'm not gluing 1,500 tiles down on this table. I don't have that kind of time. Okay? So I want to use bigger tiles, because if I use bigger tiles, I don't need as many. But here's the question. How big can I go? What is the biggest tile that I can use? What's going to help me figure out the biggest tile that will fit evenly into 30 and fit evenly into 50? give me a number. Tell me the name. How can I find what goes into 30 the same amount of times that it goes into 50? What is that called? Take a chance. You've got nothing to lose. Even if it's wrong, who cares? In a sense, it is division because I'm talking about a number that goes into it. So in a sense, it is. Euclid's method will help us find this. The GCF. Very, thank you. The GCF. So if we can find the GCF of 30 and 50, we will know the size of the tile. So if we need to use Euclid's algorithm, sure. If we need to use tree diagrams, sure. List method, sure. But I bet a lot of us know this one mentally. What's the GCF of 30 and 50? I don't want to use 1-inch tiles. Could I go by 2s? Would 2 inches go into both of those? Yeah. What about 5s?
Yeah.
Yeah. But is there something bigger? Or the biggest tiles possible? 15 will not go into 50. 10. So if I use 10-inch tiles, 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. 10, 20, 30. So go ahead and now divide your box into groups of 10. So because the GCF of 30 and 50 is 10, I knew to count by tens. I can count by tens to get 50 evenly, and I can count by tens to get to 30 evenly. Because 10 is my GCF. The GCF told me what size to use. Okay, I'm going to say that one more time because this is the key to the lesson. The GCF is the size of the tile. Because if I use 10 inches, can I go by tens to hit 50? Yup. Can I count by tens to hit 30? Yup. So that's the biggest tile that I can use. So to answer question B, if we use squares that are 10 by 10, how many do we need? How many tiles are here? How many tiles are there? So we need 15 squares. So we already know that the GCF is 10. So 10 inches by 10 inches. That's the measurement of the sides. The sides are 10 because the GCF is 10. All right. Question C. Not my question. But now suppose instead of a computer table that was 30 inches by 50 inches, suppose it was a giant chunk of cheese. Now pretend you are going to cut the cheese. Yes, I said cut the cheese. Suppose we're having a party for Mickey Mouse and Chuck E. Cheese. Those are big mice, right? So big mice, they have big crackers and big cheese. So we're going to cut the cheese to fit on the crackers for our big mouse party. Would it change anything if it was still 30? Who comes up with this stuff? 30 inches by 50 inches of cheese. Would I still cut them in 10-inch pieces?
Yes.
Would I still have 15 pieces of cheese? So the answer is no. It would not change the thinking or the calculation. So how many pieces of cheese would we make? 15. It's still 15 pieces of cheese. So I need 5 10-inch tiles to go across the top, and I need 3 10-inch tiles to go down the side. So 5 times 3 is 15. I need 15 tiles to cover the whole area of the table. I want to do another example, so please turn to your exit ticket for lesson 19. So for your exit ticket for 19, we want to find the GCF of 45 and 75. Before we get started using Euclid's algorithm to find the GCF of 45 and 75, what do I know about my answer? And I'm going to write this over in the margin because I want to make sure I have a reasonable answer. So what would a reasonable answer be?
Well, it has to be 45.
Less than or equal to 45. So if you want to put that in the margin. Now, what about 2? Is 2 a reasonable answer? It's less than 45 and 75, but is it reasonable? Why not? And so is 45. So 45 and 75 are both odd numbers. So 2 can't be a factor because those are odd numbers. So 2 is not reasonable because it's even and those are odd. So go ahead and solve using Euclid's algorithm and find the GCF of those numbers. Okay, so we're using Euclid's algorithm to solve. Gentlemen, there shouldn't be talking or whispering. Check your work. Please draw your arrows. Please finish all the way until you get that 0. Now again, some people might want to use that 2. That's the quotient, but that's not reasonable. 2 is an even number. Those are odd. So our GCF is our last divisor. So the GCF equals 15. Is that reasonable? Yes. Okay. So, God bless you. So, February vacation is coming up in a few weeks, and my husband said to us the other day, should we go visit Aunt Eleanor over February? And Aunt Eleanor is my husband's uncle. My husband's aunt. Let's make sure you're paying attention. We love Aunt Eleanor. And she lives upstate, and we love to go visit her as much as we can. And she's great. She's 85. She's almost 86 years old. She's a Spitfire. Doesn't even have a remote control for her TV. Her vacuum is 60-something years old. So it's like going back in time. But when my kids here visit Aunt Eleanor, my kids yell, Pudgy's! Because the pizza place there is Pudgy's Pizza. Not good New York pizza. And to be honest, I think it's quite gross. But we end up eating the whole thing. It's so bad it's good. Pudgy's Pizza, but here's the thing about Pudgy's Pizza. When you order Pudgy's Pizza, you order a sheet pizza. And I'm not kidding you. The box is like this big. You have to walk in the box sideways through the door. And she has this huge dining room table. And it takes up almost the whole dining room table. And we just sit there with paper plates and a whole box of napkins. But here's the embarrassing part. I end up eating like 6 slices of Pudgy's Pizza. But, if the sheet pizza is that big, alright, I'm going to say these are centimeters and not inches. I don't know exactly how big. When we go upstate in February, I'll bring a box back and I'll get the box.
Really?
So, of course. So, alright, now here's the thing. I'm going to draw a better sheet pizza here. We'll make it red because it's pizza. Now, I told you, it's embarrassing when we all finally come up for air from eating. How many slices did you eat? And I'm embarrassed to say 6. But they cut the slices really small. So what can we do so I don't have to say 6? So I can be like, oh, I have a small appetite. I only had 1 or 2 slices. How could I eat the same amount of pizza, but say it was only 1 or 2? Because they cut. So if they cut little pieces, I'm eating like 6 little pieces.
Where'd you come from?
Instead of eating 6 little pieces, how could I eat less pieces? Make the pieces bigger. So, what's the biggest slice that we can make? What's the biggest size? What's the biggest size? What tells us the size of the squares we could use? What would tell us the size of the pieces that I can cut? What, before I break the board, please, what would tell us the size of the slice? Everybody? The GCF. So if I cut by 15s, it'll work evenly into both sides. So 15 goes into 45 how many times? 3. So if that slice measures 15, that measures 15, that measures 15. You're drawing this on your paper. So then I have to go by 15s across the top. How many? 5, that's right. 15 times 5 is 75. Those are the factors. 15 times 5 is 75. 15 times 3 is 45. Whoops, that's it. So 15, 5 times is 75. 15, 3 times is 45. So the GCF told me how big to cut each slice. That's the biggest slice that I can cut. Okay? So instead of the Pudgy's sheet pizza being cut into 50, 60 pieces, where I go, I ate 6. Now, I could say I ate 1. But, how many slices are there now? How many slices are there in the pizza? There are less. How many exactly? 1, 2, 3, 4, 5 times 3.
15.
So 5 times 3 is 15. Now, this is a coincidence that the number of slices is the GCF. This is a coincidence that the side is the number of slices. That's a coincidence. So these are the biggest pieces that I can make. 15 by 15. So take a minute now and turn to problem set. You have to write down. Everybody should have on their paper. Oh, I'm going to go to the next slide. So the GCF, you're writing this on your exit ticket, is 15. The size of the side equals 15. On your exit ticket, so the number of squares is 15. I think I'm spelling coincidence wrong. That's a coincidence that 15 is the number of pieces. Because what was it on our first example? Our GCF was 10. And the size was 10. And that gave us 15 pieces also. And you're not always going to get 15 squares.
Okay.
It's just for some reason today all of our examples gave us 15 squares. So now I want you to look at the problem set for lesson 19. Take a look at number 2 and 3. 2 and 3 have A and B. A and B. So for part, why is there talking and singing? I'm trying to help you with your homework. So So take a look. You should have a pencil out. I'm trying to open this, but it's taking forever. All right. So, for 2A, it says all pieces of pizza must be square with none left over. What is the length of the side? So when it's asking for the length of the side, what are we looking for? We're looking for the GCF. How many pieces? That's asking us. You should be writing this down, boys and girls. So for GCF, you're going to use Euclid's algorithm. How many pieces? That's where you're going to draw the rectangle. The same thing for number 3. All the pieces of the square with none left over. The length of the side is the GCF. And Mr. Euclid is going to help you. How many pieces? That's where you are going to draw the rectangle. And yes, I know. I can't, oh my goodness. So for A and B, for both of them, I should see Euclid's algorithm and your square with the boxes drawn. And remember, the GCF tells you how to count when you're drawing your squares. Okay? Don't forget, there's extra help tomorrow. Today, for period 1 and 2 extra help, only 4 people showed up. Yup, I heard a lot of people from period 5 and 8 went to Learning Center, and that's awesome. But tomorrow on Tuesday, extra help with me for periods 5 and 8, extra help in the Learning Center for periods 1 and 2.